Hello and welcome back. Mrs. Saunders here. We are starting a new adventure into series and sequences. And this is a long unit, but it is so cool what we can do with math. Today we're going to review the basics of series and sequences, and then we'll really dive in next time. A sequence is a list of terms arranged in a particular order, like this: 3, 8, 13, 18. We would call 3 A1, or the first term, and 8 we would label that A2, or the second term, and so on and so forth. So this sequence of terms is symbolized by A sub n, and that n there, we call that the index. An explicit formula that would generate any term in the sequence is called the nth term expression. A possible nth term expression for this sequence could be 5n minus 2. If we wanted the third term, we would do 5 times 3 minus 2. So 15 minus 2 is 13, and yep, there's the third term. Geometric sequences are huge in calculus. In a geometric sequence, every term is multiplied by a constant number, which we call the common ratio, to get the next term. Look at this first sequence. To get from 5 to 15, we multiply by 3. To get from 15 to 45, we multiply by 3. To get from 45 to 135, we multiply by 3. You get it? The common ratio of this geometric sequence is 3. Now look at the bottom one. To get from 1 to 1/2, we multiply by 1/2. To get from 1/2 to 1/4, we multiply by 1/2. The common ratio of this geometric sequence is 1/2. If a sequence has a finite limit as n approaches infinity, we say that the sequence converges to that limit. Well, what does that mean? Look at the terms in this first one. So the first term is 1, the second term is 1/2, the third term is 1/4, and then 1/8. And the bottom of each of these fractions is getting bigger and bigger and bigger and bigger, which means each term, as we go on in the sequence, is getting smaller and smaller and smaller and smaller. The limit as n approaches infinity of this sequence is 0. The terms are approaching 0. So we say that this sequence converges to 0. If a sequence does not have a finite limit as n approaches infinity, we say that the sequence diverges. So if you look at all these terms, they're getting bigger and bigger and bigger and bigger. The limit as n approaches infinity of this sequence is infinity. So we say that this sequence diverges. So let's look at a few more of these. Each of these is a geometric sequence. And does it converge or diverge? Can we find its limit? So for A, we've got 1, negative 1/2, positive 1/4, negative 1/8. It's very similar to the one we looked at on the last slide. Now, even though it goes from positive to negative, positive and negative, the terms as they go to infinity are still getting smaller and smaller and smaller and smaller and smaller. The limit as n approaches infinity is 0. This sequence converges to 0. B, it says a sub n equals 3/5 to the n. What does that mean? Sometimes it helps to just write out the first couple terms in the sequence to see what's going on. 3/5, 9/25, 27/125, and so on. Do you notice how the bottom is growing so much faster than the top? So the limit as n approaches infinity of this sequence is also 0. This converges to 0. C, this time a sub n is 5/3 to the n. So again, let's list out the first couple terms of this sequence. 5/3, 25/9, 125/27. Now, the top is growing so much faster than the bottom, and so this guy, as n approaches infinity, keeps growing and growing and growing. So this is a divergent sequence. Now, just note for future reference, a geometric sequence will converge to 0 if the absolute value of the common ratio is less than 1. A geometric sequence will diverge if the absolute value of the common ratio is greater than 1. That's going to come in handy later. Let's look at a few more. These are not geometric sequences. A sub n equals sine of n. So as n gets bigger and bigger and bigger and bigger, what happens to the sine function? Well, it just oscillates up and down and up and down and up and down. There is no limit, so this is a divergent sequence. B, if a sub n is 3n plus 2 over 5n minus 1, what happens? Well, let's take the limit as n approaches infinity. And, oh, look at this. This is talking about n behavior of a function. And since the powers match, there's n to the 1 on top and n to the 1 on the bottom, we can just look at the coefficients. So the limit as n approaches infinity of this is 3/5. So this sequence, we'd say, converges to 3/5. In other words, as n gets bigger and bigger and bigger and bigger, the individual terms get closer and closer and closer to 3/5. What about C? 3 plus -1 to the n. So if n is odd, we're going to subtract 1. If n is even, we're going to add 1. So it would be, what, 3 minus 1, and then 3 plus 1, and then 3 minus 1, and then 3 plus 1, and just doink, 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 back and forth between 2 and 4. So the limit as n approaches infinity of this guy, yeah, doesn't exist. This would be a divergent sequence. And let's continue. We've got a sub n equals natural log of n over n. Well, as n approaches infinity, what do those terms do? If you just plug in infinity there, that is indeterminate form. So, L'Hopital's rule to the rescue, we will take the derivative of the top and the bottom, take the limit as n approaches infinity again, and you get 0. So that sequence converges to 0. You guys are getting a lot of limits practice today. Oh my goodness. How do you take the limit as n approaches infinity of factorials? Let's review factorials for just a moment. Let's say I have 4 factorial over 6 factorial. 4 factorial is 4 times 3 times 2 times 1. That's a factorial is. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So notice here, just a sec. So 4 times 3 times 2 times 1, that's 4 factorial. 4 times 3 times 2 times 1, that's 4 factorial. So actually, I could rewrite that as 4 factorial over 6 times 5 times 4 factorial. And now, those 4 factorials, oh, they just cancel out. So back to our a sub n up here. Let's do the same thing. We're going to rewrite this as n plus 1 factorial over n plus 3 times n plus 2 times n plus 1 factorial. This is kind of like my 6 times 5 times 4 factorial in our example over there. And again, those n plus 1 factorials, now those can just cancel out. And the limit now, as n approaches infinity, well, there's only n's on the bottom, so this goes to 0. That sequence converges to 0. We are going to transition now into infinite series. An infinite series It's the summation of a sequence with an infinite number of terms. So if we have this sequence here, A1, A2, A3, all the way up to A sub n, then if you add all of the terms together, it is called an infinite series. That's a lot of adding. Sometimes you don't want to add an infinite number, so sometimes we do a partial sum. A partial sum is the sum of part of the sequence. For example, we would say this is the third partial sum, and it's just the first three terms, A1, A2, and A3 added together. Practicing this, use the following sequence to find A sub 4, S sub 4. Well, A sub 4 is the fourth term, so it's right there. It's 8. Now, S sub 4 is adding up all of the terms up until A sub 4. So 2 plus 4 plus 6 plus 8, that's 20. Series, just like sequences, can also converge or diverge. So we have an infinite series. A series converges if its sequence of partial sums converges. So for example, if we have a series here, and we start listing its partial sums, the first partial sum, the second partial sum, the third, and so on and so forth, let's look at that sequence, because it's now a list of terms. If that's heading towards a particular number, then we say the series converges. It can also diverge if the sequence of partial sums, that list of partial sums, if it's increasing or decreasing without bound, then the series diverges. A quick note about index. Here we have an infinite series, and you see that it starts at n equals 1. Now the initial term of S sub n might be A sub 0 instead of A sub 1, in which case we would have an n equals 0 index and then an A sub 0 for our first term. So it really just depends on how the series is defined. Convergence or divergence is unaffected by where we start adding. What is affected is the value or sum of the series. So just keep that in mind. Does the following series converge or diverge? Well, let's start by listing out its first couple terms. So we're starting at n equals 1. So that would be 1 over 2 would be the first term. The second term would be 1 over 2 squared, and then 1 over 2 cubed, 1 over 2 to the fourth. Okay, so those are some of the first terms of the sequence. Now, if I start adding them together, I can get my series. So let's go with the first partial sum. That's it's just the A sub 1 term is 1/2. The second partial sum is going to be 1/2 plus 1/4. So that's 3/4. And then the third partial sum is 1/2 plus 1/4 plus 1/8. That's 7/8. And then the fourth would be 15/16. And it looks like it's converging to 1. Now, we can't assume it converges just because it looks like it does, but we can test it, and we'll do more on that in a later lesson. Now, for this one, what if we change the index? Instead of it starting at n equals 1, let's start it at n equals 0. So 1 over 2 to the 0, that's 1. So that means we need to put a 1 here in front of our infinite series, which means each of our partial sums would have an extra 1 tacked onto it. So instead of this series perhaps converging to 1, this series would maybe converge to 2. So it's still converged, it's just the value of the sum of the series that changes when you mess with the index. Example 5, does this series converge or diverge? Again, let's just start by seeing what happens. Let's put some terms out there. If n equals 1, we just plug in 1 for n. We've got 2 times 1 plus 1 is 3. If n equals 2, it's 5. If n equals 3, it's 7, 9. Okay. So this series is going to be 3 plus 5 plus 7 plus 9. The first partial sum is 3. The second partial sum is 3 plus 5. Third partial sum is 3 plus 5 plus 7. The fourth partial sum is 24, and this thing is just going to grow and grow and grow and grow. So we'd say the limit as n approaches infinity of s sub n, those are the partial sums. As we continue on this journey of partial sums, it's just going to infinity. So this is a divergent series. You may also see a problem that looks like this. An infinite series, so we have a summation of a bunch of terms, has an nth partial sum of s sub n equals 2n over 7n plus 1 for all n greater than 1. What is the sum of the series? Well, basically, I could know any partial sum by just plugging in an n. So I could know the fourth partial sum by plugging in 4 for n. So 2 times 4, 7 times 4 plus 1. But what I'm curious about is n going to infinity. If I add up all of the terms, what's going on? So I'll take the limit as n approaches infinity of s sub n. And that's 2/7. Okay, so this series converges to 2/7. I want to stop just a moment and talk about the difference between a sequence and a series converging. This series here is one we just looked at, 1 over 2 to the n, and we said it looks like this series is converging to 1, and we're going to learn how to test that later. But this is an a sub n, and it's basically the same thing, 1 over 2 to the n. That is a geometric sequence. There's nothing being added up. And that geometric sequence has a common ratio of 1/2, that's less than 1. That converges to 0. So if I expand it, this a sub n is each of the terms, growing, 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 and the s sub n is then adding them all together. So the terms approach 0, but the sum of all the terms approaches 1. So just think about that for a second and try not to get confused between terms approaching 0 and a series converging to 0. Now, that brings up the nth term test for divergence. So here we have an infinite series, a bunch of terms being added together. If all of the terms, if the terms are not converging to 0, then the series diverges. It just keeps getting bigger and bigger and bigger and bigger. Now, if the terms do go to 0, then the series can converge or diverge. You actually don't know yet. But at the end of the day, here's what you do know. If you know a series converges, then the terms have to go to 0, because at the end of the series, you want to just be adding a bunch of zeros together. Use the nth term test to make a conclusion about the divergence for each series. Okay, so this right here, is talking about all of the terms, and this says we're going to add them all up. So let's see what's happening as n approaches infinity to the terms. So we'll take the limit as n approaches infinity of that a sub n thing there. And let's see, we've got matching powers on the top and the bottom, so we can just look at the coefficients. So these terms, the limit goes to 3/5. That's not 0, because what we're saying is at the end of a series, we're adding basically 3/5 over and over and over again to infinity, which means the addition of all those is going to keep growing and growing and growing. So this series diverges by the nth term test because 3/5 does not equal 0. What about this one? So 1 over n, that's my a sub n. And the limit as n approaches infinity of that 1 over n, oh, it is 0. So does that mean the series converges? Actually, you don't know. There's no conclusion on this one, and we'll learn later how to tell if a series converges or diverges. But this one is actually quite interesting. Here's a graph of it, and the terms I've graphed down below here in orange. And then the black is the partial sums. So as I add all of the terms together, the partial sums are growing, 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 growing. So the terms are going to 0, but the addition of all of them just keeps growing. This is called the harmonic series. It's a special series, and we know that it diverges. And it's weird that the terms are going to 0, but it diverges, because basically the terms don't get to 0 fast enough for the series to converge. That can be a little confusing, but if you want to, go on YouTube, you can look up the proof for that. This was a long lesson. Thank you. Thank you for staying with me, and I will see you next time.